Yes? The main thing here is just visualization. This is not going to help you find the volume of the solid. Right? We're going to have to actually do a little bit of math for this. But this is just to help you visualize what's actually happening with that. Then you can take the same base. Take the same base with the parabolas. I guess it would be more like this, I suppose. Oh, come on. There we go. Yeah, it looks more like that, I guess. And you can change the cross sections. Instead of rectangles, it could be squares or circles. Let's look at circles. So if the cross sections are circles, look at that.
It's like a lemon.
Oh my goodness.
Looks like one of those Baby Bell cheeses, kind of.
Oh, yeah. No. What is it? Lemon?
So then you can see the circular cross section getting larger or smaller depending on where you are on the solid. That make sense?
What other shapes?
There are semicircles. Same thing, just half the size, right? Again, you can see the semicircle moving its way across. And then there are equilateral triangles. This is the one that looks sort of like a mohawk kind of looking hairdo. So again, you can see the triangular cross section in there, working its way across and towards you and away from you. You can see it from down here. What about the scalene triangle? I think the next one's a right triangle. Isosceles. Isosceles right triangle. So notice how the right side is vertical. That's where the two legs, the left side would be the hypotenuse. So check this out. Watch the triangle coming right at you. See it? Now it's going away from you. You can change the way it looks, the angle at least, the perspective. There's another perspective on it.
Is this related to like how you read things? Like kind of like
Not directly. Use a different programming language for that, but it's the same idea of how do you use numbers and equations to describe the shape of a solid. This is one way you could do it. Yeah. Okay, so anyways, the whole point of this is really simple, just to help you visualize. I hope that helps. You guys have any questions? Okay, so then what we can do with this, we could find the surface area of a resulting solid like that. We could find the volume of a resulting solid like that. If you knew the density of the material being used to make the solid, you could then find the mass, therefore the weight, et cetera, assuming that it's a homogeneous density. Can you imagine if the density varied depending on where you were? Just be a slightly more complicated. That'd be a Calc 3 question with more than one variable inside the antiderivative. So whatever. All stuff you can do just gets a little more complicated the more variables you add into the mix. So the only thing we're going to really focus on is the volume. And so here are your formulas. This is what we did not get to last time. The formulas, maybe those of you that are veterans remember this. These are actually really simple formulas. They're very adaptable. So if the cross sections, like the square, the triangle, whatever we just looked at, if they are perpendicular to the x-axis, the volume formula is this. Volume equals integral from a to b. And actually, let me be a little more clear. X equals a to x equals b of a of x dx. And if the cross sections are perpendicular to the y-axis, of course, it's the exact same formula, except it'd be integral from y equals c to y equals d of a of y dy. It's the same formula, just one's in terms of x, the other one's in terms of y. It does follow the same kind of principle as the washers and the discs. We're always going to be looking at what's perpendicular, in this case, to our axis, x or y. And of course, the other one's similar idea, except it's rotation. These are not rotation, but same relationship. So those are your formulas. And then the a of x and the a of y, what do those stand for? Area of what? No.
the area formula for the shape, like if it's a circle.
Yeah, area formula for whatever the cross section is. So I'll just put area of the cross section. And so the cross sections could be all kinds of shapes. For instance, if it is a rectangle, it would be base times height. If it was a square, it would be side squared. You get the idea? What if it was a triangle?
1/2.
Yeah, 1/2 BH. What if it was a semicircle? Yep, 1/2 pi r squared. I mean, the list goes on and on, not too far. But you have all these nice, regular, sort of geometric shapes that could be the cross sections. There could be all kinds of things. It could be hexagons, octagons. I mean, there could be all kinds of stuff. We'll tend to stay away from those unless the area formula is given to you. Like if it's kind of an out there a ways a little bit area formula, it would probably tell you, hey, the area formula for the cross section is whatever, and then you could just use that. That make sense?
Yes.
All right. Well, then let's do an example or two. Let's look at number 4. Number 4 says, find the volume of the solid formed with cross sections perpendicular to the x-axis that are equilateral triangles. I don't know. Let's not do number 4. Let's do. Sorry. Let's do number 5. I think, how many are there? Are there 4 of them? 4 of them, it looks like. 1, 2, 3. I guess there's 5. Let's do number 5, please. Number 5. So find the volume of the solid formed with cross sections perpendicular to the y-axis that are squares. The circular base is formed by x squared plus y squared equals 9. I am going to sketch this real quick, just to give us a sense of what this looks like. You can do the same if you want. So I see Jasmine's gone. Is that it? Yeah. Right?
Yeah.
Anybody know she's sick? I saw her at church yesterday. Nobody knows? Okay, I'm just curious. There's my circular base. Got a little squiggly there, but it worked out okay. And then the cross sections are perpendicular to the y, and they are squares. And so maybe it would look, I wanted maybe a couple of sample cross sections would look, there would be one of them for way out here on the end, be pretty small. So on and so forth. Does that make sense? Okay. Why don't you guys try? You can use that formula. Volume by cross section is equal to integral from A to B of cross sectional area. Ready, set, go. I don't know. Yeah, see if you can.
No, that's just like I heard you guys playing. Yeah. I agree. Yeah, it sounded like those songs. Oh, I thought you were gonna say it sounds really good. With this, oh, and it's a square. So they're both
Jeff, how you doing? I think it's pretty close. I think which variables you're using are a little mixed up. I think you have the right sense of this though. It should be in terms of y. Is it in terms of y? Okay, one of them looked like an x. Sometimes y's can look like x's a little bit. Hey, let's check this one out and see how it goes. So it is cross sections. You're just told that. So volume would equal the integral from where to where. So where would I start accumulating these square cross sections? -3 to 3. If we didn't want to use symmetry, we could do it this way. So it'd be the integral from y equals -3 to y equals +3. And then the cross-sectional area, well, it's a square, and the area formula for a square is what? Let's be more specific. Side times side, side squared. Simply because the sides are the same length. So I'm going to go something squared. And then the cross sections are perpendicular to the y-axis. So the thickness is, it's dy. Thickness is dy. Yeah, I get it. Okay. So then your last item to set this up would be the length of the side of the square. Any ideas on that? How long is the, like I'm talking about from this dot, from this one to this one. Like how far is that? So yeah, you're going too far. Let's bring it back one little bit. How far is it from here to there? It's x far. And so the whole thing, the whole length would be 2 of them, right? So 2x. But everything's got to be in terms of y. So I've got to replace that x with something that is in terms of y. I would then use this to do that. X squared equals 9 minus y squared. X equals plus or minus root 9 minus y squared. Do we pick the plus or the minus? Does it matter? No. Not on this one it doesn't. If it was a rectangle, it would matter. Rectangular cross section. Here it doesn't matter. I will go with plus though. So it'd be 2 times the square root of 9 minus y squared for your side length. I really don't think you need to have a calculator here. I think that we could simplify this pretty easily. Integral from -3 to 3, it would be 4 parentheses 9 minus y squared. Now you could distribute the 4, or you could just bring the 4 out. And then I would say this would be, for you guys at least, a pretty easy integrand and fundamental theorem to handle. The numbers, I think, even work out nicely, right, with the 3s, all that stuff. So I would let you guys finish that one up. Again, I want to make sure you know how to set these up. We can take it through. Did anybody take it through to an answer? What'd you get?
144.
144? Okay. So we can say volume equals 144. The fact that that's a whole number makes sense, just the way the antiderivative would work out. But, okay. So questions, especially, like, again, thinking Jaden, Jeff, you're surrounded by people that have all done this before. Do you guys have any questions about how this one worked? Okay. So let's move on to number 6 then. I think. Let's look at number 6. Number 6. Sure. So another circular base. They're not always like that. You'll see some different ones here in a second. Let's see if you guys can handle this one. A little different. Where'd he go? I hope you did. So volume equals, where did you start integrating? From where to where? -2 to 2 works. And then your area formula for the cross-section has to be in terms of x, and it's a rectangle cross-section. So the area formula for a rectangle is what times what? Okay, and we know the height is 3, so I'll just put height times base, 3 times something. Now your base length, of course, stretches from here to here, and it varies depending on where you are, right? If you're more towards the middle, the base will be longer than if you're on the ends. And so it's got to be a variable. How far is it from here to here?
Y.
That's y. And then, of course, the full length of the base would be 2y. So we're going to go 2y. But then we got to remember that it's actually dx. So I've got to replace the y with something that's in terms of x. And if you're in the habit of replacing the y mentally, that's fine. You don't have to write this step. But we'd end up with volume equals integral from -2 to 2 of 3 times 2. And then is it, what, square root of 4 minus x squared? And then, of course, times dx. Did anybody do an alternative at all to this? Or yeah.
I didn't do it, but I was wondering, could you just go 0 to 2?
Sure, let's talk about that. So you could have integral from 0 to 2 of the exact same thing. But then if you are going to do that, what else has to be part of this?
Another 2.
Yep, the whole thing has to be multiplied by 2. Of course, you're using symmetry well if you do that. Not everything is symmetrical. This one was. The other one was too. Yeah. Say again? Let's see here. This would be certainly a little tougher. Let's see here. Volume equals 3 times 2 is 6 times 2 is 12. Blah, blah, blah. So this would, I'm not going to go here because I want to keep moving. I'm guessing would be a trig substitution with sine. Why what? 0 to 2. Duh. I wrote one too many 3s. I was writing too fast and wrote a 3. I think it'd probably be trig substitution. Yeah. Or you could use a power series. Or your calculator. But yeah, I think probably trig sub. Okay. Any other questions? Okay then. Let's get away from circles. Let's do number 7. We'll come back to that one, don't worry. 7 is a pretty nice question as far as comparison between the two different ways that we found volume. This one, if I remember correctly, I'm pretty sure, oh yeah, definitely, no calculator for sure, because these are just setups, right? It says write but do not evaluate. And so this is a nice contrast between the different ways that we have found volume. So please try both A and B. One of them has cross sections, and the other one does not. All right, ready to go? Seen a few answers, and I'd like to figure this out myself. Okay, so write but do not evaluate an integral expression for the volume if r is rotated around the horizontal line y equals 1. So y equals 1 is just right up there near the top of this region. And so I'm just going to write that in real quick. So as I write this in, you get something like that. And you can see it looks like, according to that point up there, 1/2 comma 1, it looks like that horizontal line does intersect the edge of the region, like right there at one single point. But the big idea here would simply be that as I rotate around that line, the resulting solid would be very concave, right? It would have a big gap in the middle of it. And so because of that, I have to use washers. So we're going to write volume equals pi integral big R squared minus little r squared. And you really ought to start with that, right? Make sure that you show that you know that we need to use the washer method. The next thing is we got to decide on the dy or the dx. What's the relationship? Jasmine's not here to help you between the axis of rotation and the representative rectangle? Perpendicular, yeah. So perpendicular representative rectangle would look about like this. And what that does, of course, is tell us that our thickness is dx. And so that means my differential is also dx. It means that everything has to be in terms of x, which is why I wait until now to do my limits of integration, right? So if my limits of integration have to be in terms of x, my low limit would be what x value?
0.
0, and my high value would be? 1/2. I wish I had a couple bucks for every time someone mixed up the limits of integration and put y's and there should be x's. I could buy you all lunch for a month, right? Make sure. What's that? But I could like take you out to lunch. It would be special. It would be special. It was totally hypothetical. I said if.
That's going to be our Mr. Anderson's taking us
Collecting money for errors. And yeah. Anyway, and then the bigger radius would stretch from here to there. And that, of course, is simply the axis of rotation minus that function. And that function is the cubic. And then the other radius would be the smaller distance from the axis of rotation to the edge of the region. Should be like right about there. So that would be 1 minus sine of pi x. Yes, and the whole thing is squared. True. Okay, so all I had to do was set this up. That's a setup. How are we doing? Any questions at all? All right. So then for the other question, I'm going to adjust the region a little bit. Here is my in perspective y. Here is my in perspective x. And here is my attempt at drawing that region. Something like that-ish. So then my cross sections are perpendicular to the y, and they are rectangles of height 2. Something like that. Okay. Bless you. All right. So then the volume equals integral from where to where of area of the cross section. Let's first of all think about this. If our cross sections are perpendicular to the y, what would be my lower limit of integration? Where would I start accumulating?
0.
And where would I stop? 1 this time, right? Because everything is in terms of y, because I'm perpendicular to the y-axis. So it's going to be a dy thick cross section. And then I've got to put in my area formula. So we are talking about rectangles of height 2, area formula being base times height. I'm just going to go 2 times whatever the base length is. How would you guys describe the base length?
R.
The only problem with writing g of x minus f of x is that because everything's in terms of y, everything's got to be in terms of y.
Got to switch mode.
So we're going to have to do some work to get those in the right form. G is, let's see here, this is g of x right here. So this would be y equals sine of pi x. And this would be y equals 8x cubed. So what do I need to do to get to the right form? Solve for x, yep. So I'm going to put solving for x. Let's see here. Gosh, how would I solve that one with sine? How would I solve that for x? Inverse sine. So inverse sine of y equals pi x. So it'd be inverse sine of y over pi minus, and the other one would be cube root of y over 8. And as unpleasant as that is, that would be it. All we had to do really was set it up. So we're good. Questions, guys? Did you guys have this in terms of y?
Is it arc sine?
Solid?
Same as inverse of sine?
Yes. Yep.
Why do you have arc sine of pi minus? Wait, so yeah, do the other way. The function
Do the right minus the left.
the left function is sine of pi.
Since we're doing it around the y-axis.
Oh, I did flip it around, didn't I? I asked, and you all just sat there in silence.
We just wanted you to look at
Oh, well, you are really late. You are really late to that party. So
No, we were just
there we go. So let's see here. This would be cubed root of y over 8 minus inverse sine of y over pi.
Fine. F of x is y1 and g of x is y2. Can we do that or no?
Define f of x as what?
Like y1. Just like
But then when you looked for what y1 is, it's an x,
okay.
right? It's like in terms of x. Hey, you know what I could have done, guys? I could have tried to be really tricky. Couldn't I have had this original and then just said, no, now I'm right? That would have been just as correct, right? No, I erased it all and I'm back to my original switch. Or put it in absolute value. We got to be careful. You know what? In this one, it really wouldn't matter whether you put the output or the input into absolute values. That wouldn't matter either. Inadvertent mistake, hopefully something worth thinking about. Okay, anybody else the question concerned at all? That's right.
Yeah,
It's hard to see.
Wait, it is there?
I just highlighted it.
No, because he flipped it.
I flipped them back to the wrong order
Oh, you flipped them back.
and then multiplied the result by a negative. I like it the other way better, but I could have done that too. So, okay. Anybody else with a question or concern? Okay. So let's do 8. I think this is probably good timing for number 8. So check it out. Use your graphing calculator, please, to figure out what this thing looks like. Number 8. This is a lovely, lovely question, right? I like it. Okay. You guys okay with this region? Hey guys, you okay with that? It look like what you have as far as a region? Okay, so then if this purple region is a base and my cross sections are perpendicular to the x-axis and they are squares, you could draw them in and they would look something like that. Whatever. But of course, as you get closer and closer to the y-axis, aren't the bases of the squares just going to get longer and longer and longer and longer? Heading towards what? Right? Because we got a vertical asymptote right there. And so this has hopefully led you to an improper integral concept. The idea, it's going to be tempting to say, hey, those squares are going to be infinitely huge as you get closer to the y-axis. Therefore, the answer is just infinity. But maybe you remember from before, whether you get an infinity type of an answer here or a real answer kind of depends on how quickly the graph approaches whatever asymptote we're talking about. So let's set this up. You could say, like Liz had this set up pretty well at the start. I don't know how you finished, but she said integral from 0 to 16 of cross-sectional area would simply be side squared because it is a square cross-section. So you'd get something like that. And then you'd say volume equals integral from 0 to 16 of x to the negative 1/2 dx. And maybe you figured it out. Maybe you haven't yet. You got that vertical asymptote there. As soon as you figure it out, you should probably put in your limit, right? We cannot evaluate this integral without a limit. So maybe we say something like volume equals the limit as b approaches 0 from the right of integral from b to 16. You could put it in right there as far as the timing goes. Then we're going to do our antiderivative. Volume equals this limit. And then it would be 2x to the 1/2 evaluated from b to 16. And then, using our fundamental theorem, it's going to be 2 times 16 to the 1/2 minus 2 times b to the 1/2. And now this is where we could probably apply that limit. The limit as b goes towards 0 from the right. Well, the square root of something heading towards 0 is just 0. Times 2 is 0. So I get this. And then 2 times the square root of 16 is just 8. So let's say that our volume would be 8. Would be heading towards 8, I guess, right? Yes, ma'am.
So I didn't do any of the stuff, but I still got 8.
Yeah, I get it. So I wouldn't say that doing these is impossible notationally or just like pragmatically to get to an answer. But the truth is a definite integral has to be on a continuous interval. and that's not continuous. That interval is not continuous. And so you have to use limits there just from a perspective of you're misusing what a definite interval is, unless you make a limit out of it. So, yeah, I have no doubt you could get to a numerically correct answer. Just if you ever have an improper integral, you have to use limits. All right, so any questions there? Okay. So we have like 9 minutes. Let's do this. I'd like to spread this out just a little bit. Can we save that first one maybe as a warm-up for next time?
Yes.
Let's push forward into this. We are not going to be doing surfaces of revolution. I always leave it in here just in case somehow we have extra time. I was kind of fearful we were going to have a snow day today, so that makes me more fearful that we'll have a snow day in the future, which means we don't have extra days at all. So we're just going to do arc length here, okay? And I thought what I would do is give you a couple of formulas, show you where they come from, at least discuss that, and then we'll maybe do one example. That'll leave us with one example on Wednesday, and then one example of cross sections. We'll get done with that easily, and we'll have time. We'll have plenty of time. Okay? Yes, ma'am.
When's our test on this?
Not tomorrow. It's, I think, Friday. Check your calendar, though.
It's not on Wednesday.
Like, we've done all, like, the only thing we haven't done is arc length, and we're going to be done. Like, if I really, really, really wanted to, I could probably teach you this in the next 9 minutes. It's not too bad. So, formula for arc length is given down below. So, in terms of x, it's right here. In terms of y, it's right there. So this is a formula you need to have memorized, but I'm going to show you where it comes from in hopes to help you have it remembered well. So let's say that I've got a graph. I'm going to do a lot of writing and erasing, so feel free to write down as much as you want. I'm just going to use this space off to the side to help me. Hey guys, foundational stuff here. I think this will be really, really helpful for you to understand why this is and help you remember it as well. So here's a point, and there's another point. If I gave you the coordinates for those points and I asked you the question, how far is it between those 2 points? What would you do? Wouldn't you use the distance formula? Right? So we'd assume that we are tracing a straight line between those 2 points, and we'd say square root of delta x squared plus delta y squared, wouldn't we? Plug in the numbers, we're done. All right, so then what if, instead of that, what if I gave you these 2 points and I said, all right, same 2 points, no longer are they connected by a straight line. And my question to you was, if I had to follow that curvy path, how far would I go? In other words, what is the length of that curve? And this is interesting, right? Because we can find the length of a line segment super easy, right? Use the distance formula. Finding the length of a curve, you feel, well, that's very, very different. In some ways it is very different, in other ways it's not. Let me give you an example. Maybe someone would say, you know what? I have a way to do this. What if I started here and I found the distance between that blue point and that blue point using the distance formula, and then I found the distance between those 2 blue points, and then distance between those 2, that one, and then finally to the end. I took all these straight lines, found the length of those straight lines using the distance formula, and then added them all up. Would that be a reasonably good approximation? Depends on your definition of reasonably good, but it would be an approximation, right? Well, how could you improve that estimation?
Make an infinite number of...
More points, more and more and more points, heading towards an infinite number of points. You're right. And so if I did that, then instead of these blue line segments, it would be, double. I'd find the distance between those and those and those and those. And of course, eventually, if I had just put enough points in here, it almost seemed like the whole thing was covered with these points. And as the number of points does head towards infinity, the length of the line segments would get tinier and tinier and tinier. How is it that I add up an infinite number of things that are infinitely skinny? A Riemann sum, which leads us to a definite integral. That's right. So let's go back to this. And let's think about the distance formula again. and because we are going to use the distance formula. So if I started off with that basic distance formula, and I said, all right, delta x quantity squared plus delta y quantity squared, that would give me the distance between any 2 points, right? All right, so then what if we said, let's take these deltas and let's make them, like kind of like we talked about, let's make them really tiny. So in calculus, we usually designate that with like a dx instead of a delta x, right? Yes? Okay. So what if we said, we want the opportunity to squeeze down these little tiny distances to be tinier and tinier and tinier, so there will be more and more of them. And I want to add all those up, right? So now we've got a bunch of little tiny distances between A and B, whatever those are. And so I'm adding up all these little tiny distances. Is it going to be in terms of x or y? This is where we get to make a choice. I am allowed to multiply anything by 1, right? You're allowed to multiply anything by 1 and it doesn't change the value. So check this out. What if I multiplied this whole thing by dx over dx? I'm multiplying the outside of the square root. We're going to do a little tricky algebra here to get us where we want to go to get to a usable formula. What I'm going to do is I'm going to move this dx inside the radical, and I'll leave the top dx outside the radical. So check this out. You guys are all good with square roots. Like if something is being squared inside, to take it out, don't you just square root it? If something's outside and you want to put it in the radical, what do? You square it. So as that dx gets multiplied into the radical, it's going to look like this. Integral from a to b, square root, and it's going to be dx squared over dx squared, right? Plus dy squared over dx squared. And I still have that little dx on the outside. Let me finish, Johnny. I'm almost done. Inside the radical, what's dx squared over dx squared? 1. Integral from a to b of square root of 1. And this goes back to some really old algebra. If you got a fraction and the numerator is squared and the denominator is squared, isn't that the same thing as the whole fraction in whole being squared? Yeah. So it'd be plus quantity of dy dx, whole thing squared, times dx. You arrive at one of the two formulas, right? Johnny or Jack, was it a question? Johnny?
Yeah, so the dy squared over dx squared is different than the second derivative still, right?
It is, yeah, that's a great question. Second derivative is squared y over dx squared. What I just wrote. And this is kind of a misnomer. We say squared and squared all the time. They're not really being squared. It's just indicating that you've done another derivative with respect to x, but nothing's really being squared. Over here, this means little tiny change in y squared. This means little tiny change in x squared. So I know it looks really similar notationally, but it means something very different. It's a good question. So can you imagine how easy these could possibly be if you know the formula? Bottom line is, if you know what dy dx is and you know the formula, these are typically game over pretty fast. Okay? I show you that just to help you understand where the formula comes from. Bottom line is going to be just a formula that we use. So when I see you next time, we'll do a couple of examples. We'll come back around to cross sections, and that'll be it. So hope you guys have a great day.